I'm going to show you some even bigger ones here. I'm going to skip. I think I gave myself too many slides. So I'm going to show you another really big one here with Gibbs. Okay? And I'm not going to derive this full equation, but it can be shown. The fundamental equation for Gibbs. So if we start with du equals TdS minus PdV, so that's our fundamental equation, right? Then let's see here. I'm trying to show you enough that, yeah, so, okay, I'm sorry. I'm looking at the time here, and I've got time to derive this. Apologies. Let's go through it, okay? Let's start with G. By definition is H minus TS. Or, in other words, dG equals dH minus dTS. So we're going to take the derivatives of both, okay? So dH minus TdS. And the reason why we didn't take derivatives of both last time is because we played the game where we say hold this constant, now hold this constant. Okay, now I'm going to play a game where I'm not holding either of them constant, and thus I've got to do the chain rule. So dTs first gives me TdS minus S dt. So that would be my chain rule. Okay. We also know that by definition H, so 3 lines there means that's a hard definition, is PdV. And we'll also keep going here where we're not concerning ourselves with what we're holding constant yet. I'm going to do this generally, okay? Equals du plus p dv plus v dp. So we're full treatment here, okay? So now I can say that dg equals, all right, I know dh is all this, so let's write all that down, okay? So dh is all this junk. So that's du plus pdv plus v dp, okay? And that's now minus TdS minus SDT. All right? So now, applying the fundamental equation, okay? So the fundamental equation says du equals TdS minus PdV. And let's see, I've got a TdS right there, and I've got a PdV right there. All right? So now, let's see here. I lost track of where I am. Okay, so now I'm going to say dg equals. So, oh, I know what I'm going to do. I'm going to plug in du right there. That's what I'm going to do. Okay. It's Friday afternoon. You can tell by my thing that it's 4:59 p.m. Getting tired, getting ready to go have a beer. Okay, so dg equals all of this, TdS minus PdV. So that takes care of just the du. Now, plus PdV plus VdP minus TdS minus SDT. Okay, and you can see those two terms cancel, as well as the TdS. That cancels as well. And what I'm left with is another version of the fundamental equation, dg equals VdP minus S dt. Okay? Now, we can play the same game we did before. We recognize that G is an exact expression that's a function of P and T. Cool. Great. And because we know G is a state function, I'm going to say dg, because I can see that it's connected with p and t, right, is the partial of g with respect to p at constant t dp plus the partial of g with respect to t at constant p dt. And once again, doing this game reveals something awesome and powerful and unexpected. So I'm going to write both of these equations next to each other. And this reveals more the connection of physical observables to thermodynamic potentials. So for example, you can see here from this that by definition, volume, something as fundamental as volume, is actually the derivative of Gibbs with respect to pressure at constant temperature. That's really cool. That is actually what volume is in a broader sense, right? In a bigger picture sense, okay? Or what we can also see connecting these two, right? So this is how I connect these, okay? Just from inspecting these equations, right? So now we can see that this derivative, partial of g by partial of t at constant p, is by definition entropy. Really, really cool stuff. And if we were to go to put this together, I'm going to cut it off now because I think you can kind of see where this is going, but I could use this exact same thing. I could do the thermo square from this, right? I could say from here, connecting all of those relationships, okay? Let's just do it. Let's do it real quick. I'm sorry, I'm so indecisive today. So how did I do that, okay? Okay, so here's how we do that. So we know that dg equals partial of g by the partial of p at constant t dp. My handwriting is also starting to fail horribly. Partial of g by partial of t at constant p dt. Okay, so the way this works is, and I also recognized that this derivative was equal to v, and this derivative was equal to negative s. Okay? So if now I start with that derivative, v, if I say now the partial of v, which I recognized was being held at constant t, so I really want to look at the other variable, right? So that's going to be partial of p at constant t equals, so we got a negative sign, negative. And then now I'm talking about this relationship, s. And now I'm going to compare it to this side, which is constant p, right? So now I look at t, so I switch the two bottoms, right? Okay? And all of that, wait, did I get that backwards? I got that backwards. Okay, let's talk about why I got that backwards. Oh yes, okay, so I'm going to start with v. I recognize from my fundamental equation, dg equals v dp minus s dt. Okay? So I'm going to start with v. I'm going to say partial of v. And aha, yes. So v here is tending on p. I got to switch that. Now I got to switch v to t. Okay. At constant p. And then now there's the negative sign. Now I've got s. And now s is, with respect to t. Let's switch it over to p this time. Now s with respect to p at constant t. And we recognize that that is the second derivative of g with respect to t and p. Let's see if I did it right. Let me start a new thermo square. VAT UG SHP, arrow goes this way, arrow goes this way. Here's G, little horseshoe. So we can see G is sandwiched between T and P. Okay? And we know that that's going to mean derivatives at constant T and derivatives at constant P. So if I travel up the P arrow, I get partial of V by the partial of T. And then now if I travel down the T arrow, right, I'm going down the arrow, so that's a negative sign, and I end up at S, partial of S by partial of P, and yes, that all worked out. Beautiful. Okay, so we're going to move into talking about phase equilibria. These relationships, these derivatives, are going to tell us about phases. We're going to learn even more about the universe from these relationships. Okay? So these are powerful. This is powerful stuff we're talking about. Like the thermodynamic definition of volume, temperature, pressure. We take these for granted, right? We call these a state. They are, in fact, a state, right? And we see the bigger picture of what's really going on. In this case, all of this is related to the canonical description, okay? Those states come from the mathematical relationships of our thermodynamic potentials: energy, enthalpy, free energy, Gibbs and Helmholtz, okay? Awesome. I'm sure you're going to have loads of questions because this is definitely where thermo goes into crazy world. So please, I know I didn't describe any of this perfectly, so please let's have a discussion if need be. Ask me all the questions you want. Okay, folks. Hasta mañana. I'm not going to see you tomorrow. I will see you later. Okay.